So good evening to everyone. I'm going to present this work. I'm inSecure by Design IoT protocol, the ESP touch protocol, and a case study analysis from the real market, which I worked on with my advisor, Professor Massimiliano. Well, I'm going to present the basic principle behind the SmartConfig technology. That is a family of IoT Wi-Fi pairing protocols, and I'll show you the threads and the details of a particular protocol implementation that is the ESP touch protocol. A protocol that is developed by the Espressif system and today used by more than nearly 1.5 millions of devices. Then I will present a case study of an attack for a real market device and the conclusions. As you know, the number of wireless smart devices, and in particular the ones equipped with a Wi-Fi module, is continuously increasing. And according to Amazon, in 2008, more and more objects are more and more objects are being connected to the internet. And more than 50 billions are expected to be connected in the next years. Also, new protocols are being developed to simplify the configuration of these devices. And also a significant effort have been put to simplify the user experience and the user knowledge required in the configuration processes. This is usually achieved by vendors by providing a mobile companion application that is tied to these devices. As I mentioned, these protocols are often user-oriented in the sense that they prioritize the user experience and often are not well secured. So the basic question we try to address with this work is if these protocols are secure and whether people are aware of the security risks to which they are exposed. So for what concerns our contribution, we focused on technical analysis of the SmartConfig technology. To this extent, we propose a systematic approach for the analysis of these protocols, as well as a detailed threat model and risk analysis of these threats. Also, in our case study, we analyzed a particular protocol implementation for a class of devices that led us to disclose a vulnerability and instrument a proof of concept attack against this protocol. Finally, we also suggest a set of recommendations and mitigation. Okay, although several Wi-Fi pairing protocols exist for several headless devices, this can be grouped into categories. Those that use directly the Wi-Fi stack and those that involve other transmission technology to achieve the same result. For the first case, we have the access point mode, the SmartConfig protocol. Well, for the other transmission technology, you can think about the Bluetooth or the Bluetooth low energy and so on. Let's see two examples. At first, let's look at the access point mode. Consider the scenario in figure. As expected, initially, the device is not connected to any network, but it is instead booted in configuration mode. And it starts to act as a Wi-Fi access point. This way, a smartphone that usually is equipped with a companion application can connect to the Wi-Fi, to the IoT Wi-Fi access point and configure the device to be connected to the wireless router. Basically, it configures the device with the network credential of the target Wi-Fi network. Well, next, both the smartphone and the IoT device can connect to the Wi-Fi network and possibly to the internet. But this one is the first Wi-Fi pairing schema adopted by the IoT devices, although many non-technical users still find it difficult to interface with. So an enhancement from the point of view of the usability and user experience is to use another communication channel that in this case is the Bluetooth low energy, but in a transparent way to the end user. In this scenario, the smartphone is already connected to the Wi-Fi network and sends its network credential to the IoT device, but through the Bluetooth low energy radio interface. Then the device can join the target network and connect to the cloud platform. However, this solution requires the IoT device to have an extra module used only during the pairing process, and it's a waste of money from the vendor's standpoint. However, this kind of pairing schemas also are subjected to other classes of threats. Well, the SmartConfig technology represents a good solution both in terms of cost and usability, because it combines the usability of the Bluetooth Low Energy approach and the use of a single Wi-Fi chip from the access point mode. With this technology, the smartphone sends network credential on the same target network, whereas the device from the outside grabs the credentials and joins the network. Well, as a prerequisite, no prior connection is required between the device and the configuring smartphone, and the smartphone must be connected to the target Wi-Fi network, so it must be already paired. The SmartConfig exploits the requirement to transmit both the source and destination addresses, as well as the length value of each Wi-Fi packet as a plain text, either on open or on protected Wi-Fi networks. This constraint is used by the SmartConfig family to create a cover channel and circumvent the Wi-Fi encryption. So it is able to transmit data even towards an associated wireless station. Packets are transmitted as a multicast UDP streams, where packets are constructed in such a way to have the proper lengths. On the other side, the IoT device must monitor the Wi-Fi spectrum, grab those packets, decode them, and join the Wi-Fi network. It's important to note that that data can only flow in only one direction, from the smartphone to the network, or from the smartphone to the Wi-Fi, the IoT device. And this is the reason of multiple security threats. Also, it implies that a highly structured and predefined data encoding schema, as well as a synchronization schema, is strongly required. Well, we constructed a threat model by identifying the threats that affects the asset involved in the SmartConfig protocol, and that are the user smartphone, the Wi-Fi network, and the IoT device. The agent, the only agent we considered, is a physical threat agent, since it must be placed in the close proximity of the victim's Wi-Fi network. If you look closer, the threats range from the information disclosure of addresses or other valuable network information, to the tampering in terms of message injection, to the denial of service. But if you look closer, there is a threat that could expose the Wi-Fi credential if the communication link is not adequately protected. Note that this threat does not affect the IoT device, but if exploited, it would lead an attacker to compromise the full user network. This is the threat we will focus on in the next slides. So, since the SmartConfig technology is a family of protocol, let's now consider an instance of this family. And a particular SmartConfig protocol has been proposed by the Espressif system, that is a semiconductor company specialized in the production of low-powered Wi-Fi and Bluetooth system on chips. Among their products, there are the ESP8266 and the ESP32, that are two of the most common chips integrated into several Wi-Fi-enabled IoT devices. According to their annual report, more than 143 million of devices were sold only in 2019. And in the 2015, they introduced the ESP Touch protocol, that is their own implementation of the SmartConfig technology. But before analyzing the ESP Touch protocol, let me introduce the methodology of analysis and the challenges that must be addressed. So the SmartConfig is not a formally defined nor a standardized technology, and it comes from the industrial world, so very few references are present in the literature. And as a family of protocols, the protocol implementations can present heavy differences among vendors, and no documentation or useful description are generally available about the particular implementation, as vendors try to keep them secret. And as a consequence, it is difficult to define a general and tailored at the same time strategy of analysis. However, we define a systematic methodology based on a multi-target reverse engineering approach. In more details, the SmartConfig provides a broad surface of analysis that include network packet flows, the mobile companion application, and the firmware images of the IoT devices. So a systematic protocol analysis will consider one or more of the following tasks that are based on the analysis of the raw network data streams, the compilation of or the debugging of the mobile application, and the same for the device firmware image. Regarding the ESP touch protocol, Espressif currently maintains a GitHub repository that is public, with the software materials for the ESP chip family, with 2 mobile source code, one for the Android and one for the iOS platform. So before looking at the particular implementation details, we will look at the basic protocol operation through this sequence diagram that describes the human application device interaction steps. We have 3 actors in this diagram that are the user, the Android application, so the Android smartphone equipped with a mobile application, and the IoT ESP device. Well, to put it simply, the device is booted in configuration mode at step 1, and it starts to monitor the Wi-Fi spectrum. Then the user instructs the mobile application with network tag credential to be transmitted over the Wi-Fi network, and the mobile application sends them over the network. At this point, the IoT device can grab the credential and join the target network, then acknowledge back the result of the connection status to the mobile application. From step 11, the user is able to control the remote device. Well, as anticipated, since the communication channel is unicast, the protocol requires a synchronization schema to align the 2 endpoints. The ESP touch defines 2 sequences that are encoded in the length fields of network packets that are the guide code sequence and the data code sequence. The guide code sequence has 2 purposes. The first one is to align the receiving device on the right Wi-Fi channel and to the sender. Since the in password protected networks, the encryption linearly influences the length of transmitted packets in a way that each packet is longer than the original by the offsets that are listed in this slide. Since the guide code is fixed, this is the guide code, are 4 numbers, and is always the same, a device will look for a fixed and repeated decreasing pattern in subsequent packet lengths, which remains preserved even in the presence of the encryption shifts. The data code sequence, on the other hand, represents the actual information that is being sent and transmitted by the protocol. For error detection purposes, packets are sent to continuously changing multicast destination addresses and following a fixed pattern. But to better understand the previous slide, we propose here a network capture obtained thanks to Wireshark of an instance of the ESP touch protocol. The upper part shows the guide code sequence, whereas the lower the data code sequence. The upper part, if you look at the length, should start at 515, but if you look closer, it starts at 645. This must be addressed to the fact that reported lengths are referred to the total network envelope sizes. That includes also some extra headers added by Wireshark. However, if you subtract the right values, you can calculate the proper encryption offset, that in this case is 16, because the test network was protected with a WPA2 password. Okay, here is reported the basic data schema and the encoding block performing some basic byte manipulation operation. If you look at the table, apart from the different field size, the basic information carried by the protocol are limited to the smartphone IP address for the acknowledgement, the Wi-Fi password, the Wi-Fi SSID, the Wi-Fi BSSID. If you look at the base encoding block, it involves just byte splitting and combination operation, and also a final constant sum. Here you can see that each byte is exactly 3 times the original one, is encoded in 3 bytes. Also, we noticed that the code base also implemented an advanced encryption standard class that, however, was never used. But until this point, we focused our analysis only on the mobile companion application analysis and on the analysis of the network packet flow. These two approaches proved to be sufficient also to predict the protocol behavior on the device side. For this reason, we avoided to reverse engineering the SDK and the device library. However, we decided to model the device behavior with this finite state machine diagram. The upper part is devoted to recognition of the guide code sequence, and in this state, the encryption offset can be computed, whereas the lower part is devoted to the data code collection. The structure could be adapted also for the analysis of other SmartConfig protocol implementation, although it would be necessary to modify the number of states and the evolution constraints. But at the end of our analysis, we noted that no particular design countermeasures were put in place to mitigate the threats we listed previously. And although message injection and the denial of service are still feasible, the last point is the most crucial one, since it would compromise not only the device, but the whole user network. And although the ESP touch from Espressif tries to address the eavesdropping threat with the advanced encryption standard encryption, it fails at least to indicate a key exchange protocol. So for our case study, we selected the SONOFF device, which is one of the best known and most popular smart power switch device. It can be connected to virtually every appliance. It's based on the ESP8266 chip. It can be remotely controllable through the EWLink mobile companion application. EWLink is not a basic application, it's actually a hub platform that supports more than 80 brands. But a supported device, in order to be paired to a Wi-Fi network, must be configured through the application, the mobile application. The recommended pairing option is the Wi-Fi pairing mode that runs a particular implementation of the ESP touch protocol. After applying our methodology, we found that there were some dissimilarities in the data sequence compared to the original SCP touch data structure, and also that the mobile application was not obfuscated. But the most concerning parts is that they removed the support for the BSSID field, and also they supported the hidden networks. Well, most interestingly, they introduced their own data encryption layer, which consists of 2 static index-based and interleaved Caesar ciphers that in particular +7, a shift of +7 for even letters and +2 for odd letters. Well, besides the weaknesses of this cipher, the real problem is that this corresponds to basically statically wire the encryption key, in this case the rotation shift, inside both the application and the supported IoT device. To demonstrate the feasibility of the attack, we created a proof of concept script to decode the Wi-Fi credential on the fly. The script is based on the automaton that we presented earlier. And this is a basic test bed that use a Wi-Fi access point, the mobile application and a smartphone, and the joining device. You can see that the application, this is a screenshot from the command line application, is able to decode and decrypt the Wi-Fi credential. Well, consideration since the EWI-Link provides its own SDK for also to other partners, the same vulnerability is expected to be present also in all the other supported ESP-based devices. The encryption keys, regardless of the chosen crypto algorithm, must not be statically wired inside the device and the public companion application. But it should be clear now that the main limitation is the unicast nature of the communication link. It prevents the implementation of any key agreement protocol. And also, we reported this vulnerability to EWI-Link and ETHEAD, and also published this vulnerability with a public CVE. A possible solution would be to use a separate out-of-band communication channel to exchange also a unique secret, unique for device, per device. So it could be possible to attach a sticker on each device with this unique key, or also a QR code, and require the user to manually import this key or scan the QR code through the companion application. Also, there are some problems because this approach will be not backward applicable, and must be found a solution to what would happen if the sticker gets lost. Or you can simply avoid to use this authentication schema and fall back to a more secure pairing protocol. So what's the lesson learned? First, you should not statically wire the encryption keys inside the end user's device or the application, because security by obscurity can protect you. You must use a secure key exchange protocol and also a secure encryption algorithm. And vendors must perform a deep threat analysis prior to shipping to the market, because post-solution could be not always applicable without breaking backward compatibility. To conclude, for future works, we plan to examine the feasibility of other attacks, such as message injections, and to prove the assumption we made on the device side. We noted that also other vendors implemented their own version of the SmartConfig protocols, and we are also working on a model to automatically detect the SmartConfig protocol implementation, and also to discover the encryption if present and the encoding schemas that are potentially implemented. And that's all. Thank you.